Okay guys, so I want to have a quick look at the chemical periodicity lab, and I'll just pop that up now. Here it is. And so what you've got is you've got this lab report here. It says print it out. You don't need to reproduce it, but you don't need to print it out. You can reproduce it on paper if you want to, but you need this lab report where you're going to put in your data and also answer some questions. And then there's a little bit of a blurb here, but it's really about recognizing that chemical and physical properties of an element can often be located from the position of that element on the periodic table, because the periodic table was constructed such that elements that are most alike are nearest one another on the periodic table. And in particular, elements that are in the same group tend to be quite similar to one another. Right, with a sort of like, as we move up and down the group, there's going to be a gradual trend in the exchange of properties. As we move across a period, there will also be a change in the properties, but it tends to be more dramatic. So you're going to look at the activity of metals and also the reactivity of non-metals, in particular halogens. And so what we know about metals is metals like to lose electrons in chemical reactions in order to obtain a noble gas configuration. So when we're talking about the activity of metals, we're really looking at the ease with which metals lose electrons. And so that's interesting, right? And then the non-metals, we're looking at the opposite, right? Non-metals love to gain electrons in order to obtain a noble gas configuration. So when they react, they tend to gain electrons and become anionic. So more reactive non-metals will do that more readily. So it gives you a little blurb about each of the videos that you're presented with, and it tells you that if a metal reacts with water, it will make a metal hydroxide and hydrogen gas. So we can detect the formation of hydrogen gas. Because it's a gas, it'll create bubbles. And hydrogen gas is actually a flammable gas. Another way of detecting hydrogen gas would be to burn it, and it burns with a characteristic pop. Now, hydroxides have an interesting reaction with a thing called phenolphthalein. And phenolphthalein will turn pink in the presence of hydroxide. So if there's a significant reaction of a metal with water, you'll see a pink color forming, and you'll also see hydrogen gas being formed if we have phenolphthalein present. So that's not too hard to understand. And so very reactive metals will react with water. Less reactive metals will react with strong acids. And in this case, we're going to be measuring it or observing this reaction with 3 molar hydrochloric acid. And what happens when metals react with hydrochloric acid is it will make a metal chloride, and metal chlorides are soluble. So the metal will kind of like reduce in mass. It'll begin to dissolve, and it'll also make hydrogen gas again. So you'll see bubbles, right? So that's what we're going to do for the metals. And the metals is pretty easy to understand. So we'll have a look at these videos in a moment. But first of all, I just want to, kind of like keep in mind our strategy here, right? We're looking for trends on the periodic table. So we really want to be observing like what is going to happen as far as reactivity as we head down a group and as we head across a period. Can we see any patterns there? And something that we know about the metals is as we head down a group, the ionization energy decreases. It becomes easier to remove an electron, right? We also know that as we go across a period, the ionization energy increases. It becomes harder to remove electrons. So perhaps our expectation is going to be that as it gets easier to remove electrons as we move towards the bottom left of the periodic table, we might expect that reactivity of metals increases this way, right? Reactivity of metals, as it becomes easier to remove electrons, which is what metals like to do. They like to lose electrons when they react. As that becomes easier as we move towards francium, we might expect reactivity to increase in that way. And we're going to kind of have that in the back of our mind as we look at this. So we actually look at 6 different metals, I think it is. We look at magnesium and calcium, and then we look at iron, copper, zinc, and then there's tin. Okay, tin. So tin is way over here. So there's some interesting things going on here. We've got different families or different locations of these metals, right? So we've got magnesium and calcium, which are in the same group. So that might give us information about how reactivity changes as we move down a group. And then we've got we've got S block elements, we've got D block elements, we've got P block element there. So maybe we can kind of see some difference in reactivity as we move to the different regions of the periodic table. But we're also across calcium, iron, copper, zinc. We're moving across a period, aren't we? And we can have a look at how reactivity changes as we move across the period. So that's going to be kind of, that'll be interesting, all right? So let's have a look at the video and see what happens. So in the first video, we're going to react our metals with water, okay? And I'm just going to mute it. And so into the water is going to be added some phenolphthalein. And the phenolphthalein is in that little dropper bottle there. And so he's pouring out some just, plain old distilled water. I'm going to speed it up a little bit. There's no reason for it to be this slow. We can pause, of course. Put a few drops of phenolphthalein, and that's going to turn pink if we form a metal hydroxide. So we've got them in the order tin, iron, magnesium, copper, zinc, and calcium. And we're looking also, perhaps the metal will dissolve, and we should see some bubbling if we've got a reaction going on. I'm not seeing anything at a bit of pink on the magnesium, almost immediately. There you go. So 2 really strong reactions that are very, very obvious. Calcium is by far the most reactive. And then magnesium is reacting slower. And hopefully we've got another couple of minutes to go, and we'll get to have a good look at the others up close. But clearly there is calcium is the most reactive, and magnesium is still kind of just slowly turning that phenolphthalein pink. All right, there it is. All right, and you can see that the calcium did actually dissolve. Oh, there we go, getting a bit more pink. Now, what about the other ones? Having a closer look at the zinc, nothing there. Sometimes you see the reflection and you think it's actually a color change, but it's not. I'm going to get a look at the magnesium is clearly pink. Not seeing anything on the iron. I think those bubbles are just typical for when you pour a liquid into glass. You sometimes get a few bubbles. I'm going to get to see a close-up of the copper. No, that's unfortunate. It would be nice to have seen the copper. I think we're seeing a little bit of a reflection on the copper of the pink from the magnesium. All right, so that's that. So now we have to record our observations for that, all right? So some of them have no reaction, so you can just label that as no reaction. So I didn't see a reaction for that, for example. And you need enough detail that it's clearly obvious what the difference is between the metals. So the 2 that reacted were the calcium and the magnesium. So it needs to be a reasonable description. So what happened to the calcium? Strong bubbling, instantly turned dark pink. Metal dissolved, right? And then the description for the magnesium needs to be enough to be able to distinguish it from everything else and the calcium. So you can't just do like bubbles, right? That's not helpful. All right, it needs to be a reasonable description. All right, so it doesn't need to be over the top, but it needs to be that, you know, a sensible description. So I think that what we figured out is that the calcium is most reactive, and then the magnesium is the second most reactive, right? Okay, and then you can't really do anything else. But remember what we said, magnesium and calcium are in the same group. So it seems that reactivity is increasing as we go down a group, right? Reactivity is increasing going down a group, and that's nice because the ionization energy decreases as we go down a group, and that's what we would expect. So at present, we've got this kind of trend that reactivity seems to be increasing as we go down. Now, magnesium and calcium are also the furthest to the left on the periodic table, right? The furthest to the left. So it seems as though it's corresponding with reactivity increasing as we move to the left, right? Which is good because, again, that's the direction that ionization energy is decreasing. So, you know, most reactive is going to be down here is what we're seeing so far. So everything is as we might expect. So now, to see like the order amongst the less reactive metals, what we're going to do is we're going to react them with 3 molar hydrochloric acid. And we might get some of these other ones to react. So let's have a look at that video. So this is the reactivity with the 3 molar HCl. And again, we can kind of speed it up a little bit. So we've got each of the metals are in there. Okay. Looks like it's in the same order. What we're looking for is bubbling, and we're looking for the metal sort of dissolving. We're not going to see the pink color this time because we don't have the phenolphthalein in there. So the magnesium strongly reacts, which is what we would expect because it reacted with the water. Anything that reacts with the water will also... Oh, and there's zinc. So now we didn't see zinc before, and you'll have to call it. Do you think zinc is acting more or reacting more or less than the magnesium? I think it's a little less, and calcium again is the most reactive. So the others are slower. So we already kind of got an order here. We've got calcium, magnesium, zinc is kind of the order of reactivity here. And is anything else happening? I'm thinking that I'm seeing some... Oh, the magnesium is completely gone. It's totally gone. So that's interesting. Oh, there's the zinc is getting going. As it warms up, it starts reacting a bit quicker. Let's have a look at the copper. Nothing. Absolutely nothing. Now, what about the iron? Little bubbles, right? Little bubbles on the surface of the metal there. Little tiny bubbles. So it looks like we've got calcium, magnesium, zinc, iron. And then the tin, nothing. All right? Nothing. Oh, the calcium's like foaming. There you go. All right. And the magnesium stopped reacting because he didn't put enough magnesium in. Magnesium's kind of expensive. He only put a little bit in. All right. So that's that. All right. Cool. So I think that we were in the order here that the reactivity order was like calcium was more reactive than magnesium, which was more reactive than zinc, which was more reactive than iron, and then who knows about the tin and the copper, we don't know. But you know what? If we can observe a trend kind of across here, then maybe we can extend it to assess the reactivity to distinguish and place those in what we might expect would be the order of reactivity, right? If we had another reaction, maybe we could use some stronger acid and then see if we could get one of tin or copper to react, then we would be able to experimentally verify the order of reactivity. But perhaps what we can do instead is we can use the trend that we see amongst the ones where we have strong experimental data to predict the order of reactivity for copper and tin. So if I look at this now, is it kind of consistent with what I was saying before from the water, that as we move down and to the left, that reactivity increases? And it is, with really one exception, is that this the zinc here is unusually reactive, isn't it? Right, unusually reactive, which is that's somewhat surprising. So that general trend of increasing reactivity towards the bottom left corner of the periodic table is correct, but the tin is kind of bucking the trend. So if I use that trend of increasing reactivity this way, I'd probably put the reactivity of I'd put copper as being well, it's kind of difficult, isn't it? Copper is over. It's sort of hard to tell as to copper and tin, because tin is lower and then copper is further to the left, but we know that properties vary more as you move across a period than they do down a group. So it's one space down, but it's like 4 spaces over. So I would put, tin as being the less reactive is what I would say. We only moved 1 space down, but we moved 4 over. So therefore, I would say that the moving across the period, which results in bigger changes of properties than moving down a group, that's going to be the dominant effect there. So that's what I would put for my sort of reactivity order. Now again, you need to fill in this table here with your experimental data. And some of them, 2 of them, your tin and your copper, are going to be labeled no reaction, and then you need enough detail in the rest of your descriptions that you can clearly understand that the calcium was the most reactive, the magnesium was the next most reactive, then the tin, and then there was a little few bubbles on the iron. All right, so just make sure you actually answer the questions. Look for the question marks. And then here, this one here, based upon your observations, right? Whatever ranking order you come up with, we're not saying give the correct order. We're saying based upon your observations. So if you just Google the order, you could get this wrong, because it needs to be on the basis of your observations. And then it says, identify at least 2 trends you see between the reactivity of the metals and their position on the periodic table. So things you're going to put in here is like the region of the periodic table. So is it in the S, P, D, F region? The period, the group. Does it have like a complete D shell? Complete versus incomplete shell? Stuff like that, right? And you have to pick 2 of those, okay? And they have to be, solid trends, right? Okay, so it doesn't really matter. And if you can relate it to things like ionization energy and atomic radii and stuff like that, if you want to, all right? But 2 trends that we see between reactivity and some quality of where they are on the periodic table. Okay. The next bit is about the reactivity of the halogens, and it's quite complex. So the halogens are non-metals, right? So non-metals like to lose electrons. So how we can judge the reactivity of halogens is by their ability to what we call displace a halide ion from solution. That is to turn an ion into the neutral molecule. Right, to remove electrons from the ion and have it go back to being the neutral molecule. And so what's going to happen is, I'll just flip over, is you're going to, in every case, react a halogen, in this case chlorine, with a halide ion, in this case bromine. And these guys are going to kind of like fight over these 2 extra electrons here. They're going to fight over these 2 electrons that are over here, these 2 negative charges. And the more reactive halogen will win out and get the electrons. And so that tells me that this is less reactive and that this is more reactive. whatever ends up with the negative charge when you pair these guys up is the more reactive of the pair. So what we're going to do is we're going to do a bunch of combos. We take chlorine with bromine, but we're also going to take chlorine with iodine, and we're going to see what happens. We're going to take bromine, and we're going to combine it with iodine, and we're going to see what happens. We're going to take bromine, and we're going to combine it with chloride, and we're going to see what happens. And you guessed it, we're going to take iodine, combine it with chloride, see what happens, and iodine, and combine it with bromide, and see what happens, right? So that's what we're going to do. So then the question becomes, we need a mechanism by being able to identify what ends up neutral and what ends up with the negative charge. And so what we're going to do is we're going to establish a system where we have two immiscible liquids. We have a bottom layer and a top layer. The bottom layer is the more dense layer. It's going to have water in it. And in the water will be your ion. So either chloride, or bromide, or iodide. And then the top layer, the less dense layer that floats on top, is going to be cyclohexane. And it turns out that ions are not very soluble in cyclohexane, so they won't go into the cyclohexane. But what is soluble in cyclohexane are the neutral molecules, the chlorine, the bromine, and the iodine. And the other really convenient thing is that these guys all have distinct colors. So what we're going to do is observe the cyclohexane layer color, and that tells us what is the least reactive of the pair of halogens we're combining. Now, the first thing that we're going to do when we set this experiment up, though, is we're going to run a few controls. We're going to take chlorine and we're going to combine it with chloride, and that's going to be just our control. And the reason for doing that is we want to know the color, right? So obviously it's not going to do anything because you have two of the same halogen, but we want to observe that color. This is our control for chlorine. It's going to tell us what the color of chlorine is in cyclohexane. And we do the same for bromine. That's not correct. And obviously it's not going to do anything, but it's going to give us our control for Br2. And then they're going to do the same for iodine. And so we just, like I said, we're just getting a control. All right, there we go. That'll be just our control for iodine. And then when we do the other combos, we will know, because these guys, chlorine, bromine, and iodine, have distinct colors, whether we've got chlorine, bromine, or iodine in that top layer. So your data collection, when we watch the video in a moment, you'll see it's pretty simple. All I have to do is record the color of the top layer, right? And then these ones here, this one, and this one, are basically your controls, okay, that allow you to identify what the color of chlorine is, bromine is, and iodine is in that top layer. So let's have a look at the video and see what we are going to do. Because it's a lot, right? It's a lot to take that all in. So here's the video, only 2 minutes, but I'm going to let it play at normal speed this time. So he sets up solutions containing chloride, bromide, and iodide ions. 3 lots of those. This is in water, okay? There we go. So 3 lots, 1 set of chlorine, 1 set of chloride, 1 set of bromide, 1 set of iodide times 3. All right. Now he's going to add chlorine, Cl2, to 1 set. There you go. And like I said, nothing much happened, right, to the one that had chloride ion. Then he does the same. He's adding bromine, Br2, to the second set. Okay, cool. And then guess what he's going to add to the third set? I2. Here we go. All right, so just like we said. There it is. Okay, now it's hard to see what's going on here. So now what they're going to do is add cyclohexane, and this is where we're going to get our data. And the cyclohexane is going to float on top. And he's going to give it a good shake once it's got it all added. And we're observing the color of that top layer. So you're probably going to end up pausing the video, right, to get those colors recorded. Okay, there we go. And he'll do all 9 of them. So there you are. All right, so let's just pause that for a moment. And what you want to see is that the chloride with the chlorine, that's your control. So if you see that color in the top layer, that tells you that Cl2 is in the top layer. Okay? All right. Now here's your bromine with bromide, and it's this kind of like orangey brown color. If you see that in the top layer, that tells you if you've got Br2 in the top layer. Okay? All right. And then here's your I2 with I minus. If you see that kind of pinkish fuchsia color, that tells you you've got I2 in the top layer, which it looks like you do for all 3 of these guys. Whatever the color of the top layer is, tells you the least reactive of the pairs that you're combining. So when I combine I2 and Br minus, I see pink in the top layer. It tells me that I2 is less reactive than Br. All right? Okay, when I can combine I2 with Cl minus, I get pink in the top layer. It tells me that I2 is less reactive than Cl minus. So it looks like I2 is my least reactive. All right, so you should be able to figure this out. So I already know that I2 is less reactive than bromine, so I don't have to worry about that one. This is just my control. So what is more so my control, so bromine is brown. So if I see brown in the top layer, it means I've got bromine. So when I combine chlorine with bromine, I find out that bromine is less reactive than chlorine. So it looks like I2 is the least reactive. A bromine is more reactive than I2, but less reactive than chlorine. I've already figured out the sequence. So now I just have to see whether my results are consistent when I come to chlorine. I said that chlorine should be the most reactive, so I should never see this clear color in the top layer, and I don't. So it looks good. Now, I should point out that the I2 color, you can see here, this is I2, it looks like, but it's just really, really dark, right? So you're not seeing it very particularly well. All right, so for your results there, like I said, you just got to record the colors of the top layer in each of your 9 test tubes. So when it comes to kind of grading this, I think it's important that you recognize where it's asking here, explain your reasoning, that I'm looking for your reasoning being explained in terms of the chemical reactions that are occurring rather than just sort of the color changes, right? So you should be saying that and you should, if possible, give the chemical reaction that occurred. And so, is chlorine more reactive than bromine or iodine? And we can say, we know that chlorine is more reactive than bromine or iodine because we saw these reactions occurring and giving the chemical reaction. So that kind of level of detail, not a superficial explanation. So for these questions here, it's all about how you explain your reasoning. That's what the important thing is for me. So then you're going to rank the halogens, and hopefully you get them in the correct order, the most active one first, so in order of decreasing reactivity. And then we haven't actually studied fluorine, but it's going to be kind of like what we did for tin and copper when we were looking at the metals. You have to extend your trend and predict what you would expect for fluorine. And that should be a relatively simple process. Now, when you think about the reactivity of nonmetals, on my periodic table, what do nonmetals like to do? They like to gain electrons. They don't like to lose electrons. So we would hope that the reactivity will kind of increase in the order in which electron affinity or electronegativity increases. And so what we know is that both of those things increase as we go up a group. So that's something that we might expect, is that the tendency to gather electrons increases as we go up a group. So we might expect that reactivity increases in a similar way, because electronegativity and also electron affinity, both measures of the tendency to gain electrons, increase as we go up a group. All right, let's see what happens when you look at that. Now, we're not going to be looking at astatine in these halogens because astatine is radioactive. So sometimes, but you could probably predict the reactivity of astatine once you've looked at chlorine, bromine, and iodine. Okay, that's all I've got. I hope you found that helpful.